Hi, everyone, and welcome to PyData Global 2025. Thanks for joining us today. I'm excited to introduce Jim Dowling, the CEO of HopsWorks, a longtime presenter at PyData conferences. If you know him, you love him. We're glad you're here, Jim. We're glad the audience is here. We encourage you to interact in the chat feature, which is on the right side of your screen. Also have a Q&A option, so we'll do that at the end of the session. If you have any questions, feel free to drop those there, and we'll address them towards the end. But without further ado, Jim, the floor is all yours.
Thanks, Tamara. Great to be here. Hi, everyone. Welcome to you wherever you are around the world. I'm going to talk about the journey from feature engineering to context engineering. Many people have a background in machine learning at PyData. They're interested in building agentic systems. I'm going to talk about a lot of the techniques from feature engineering that are applicable to context engineering. I'm going to talk about it in the context of building agentic applications. So I'll start with the fundamentals, which is there is a new class of machine learning exhibited in large language models, or LLMs, which is called in-context learning. So on the right-hand side, we have two different stones. One is called Lumerite, and those are called Zeronite. And in machine learning, what we would try and do is, given some examples of these stones, so given some features, such as the color of the stone, its hardness, whether it glows under ultraviolet light or not, we'd classify the stone as Lumerite or Zeronite. And here we have three examples of different stones with different feature values. And in traditional machine learning, we would train a model, a binary classifier, and given some new features, here we have a new stone, we'd like to classify it as light gray, hardness 5.5, it doesn't glow under UV. What is it, Lumerite or Zeronite? Now, Lumerite or Zeronite do not exist, but if you paste this into ChatGPT or any other LLM, it will actually work. It will be able to correctly classify the stone based on the features and values that we provided and the examples or samples that we gave with the label here of Lumerite or Zeronite. So this is called in-context learning. You have to pass all of the examples in with your question. Here we're asking, what's this type of stone? But I pass the examples into the prompt, so we don't have a separate training phase. We just do it in a single pass with the LLM. It's called in-context learning. Now, in-context learning is important because if I have a ChatGPT, or chatbot, I've got a chatbot here where we have a user who asks a query. The way chatbots work is that we'd have a static system prompt that we would add to our query. So, for example, we might say that please be nice in your responses, don't be vulgar, don't do anything which is against my policy. And then you ask the query, the LLM will give you a response. But if we have some data that's not included in the LLM's training data, so the LLM doesn't know about that data, if we want to include a relevant subset of that data into our prompt that we send to the LLM, we can call that data the context data. And the purpose of context data is to help the LLM provide a better response to a query. And it will do that using in-context learning. So context data is the data we inject into our prompts, and in-context learning is one of the mechanisms we can use to help fulfill tasks and have agents do the work that we want them to do, which is to provide better responses to queries. Now, getting private data that's not in the LLM's training data set, into an LLM, context engineering is what I'm going to talk about primarily today. You can also have static data included in your prompt. We call that prompt engineering. Or you can fine-tune a large language model with supervised fine-tuning or some variant of reinforcement learning with humans involved. And I'm not going to talk about supervised fine-tuning of large language models today. It'll be primarily about context data. And the reason why is because we see a lot of applications now using context engineering to solve problems. Klarna are a well-known buy now, pay later provider, and they claim that 65% of their customer service calls are handled by agents, and those agents use private data. So LLMs are not trained on Klarna's financial transactions. They don't know anything about them. You could say, well, I could fine-tune a large language model on their private data, but we'll see that context data is an easier way to get started, and it's also more interpretable. So it's easier for someone to debug and say, well, I know what context was inserted into the prompt, so I can understand why the agent answered the way it did. Context data is also important where we can't use supervised fine-tuning, which is real-time context data. So obviously it takes a long time to fine-tune a large language model, a foundation model. But if we have an application like a video application like TikTok, you're clicking on buttons, you're liking videos, you're sharing, you're swiping, you're viewing, that metadata, the clicks and actions that you take, can be used as context to help agents do something intelligent with your application. And that data needs to be very fresh, otherwise it won't be relevant to the application. So your click is only maybe relevant for 10, 20, 30 seconds. We need to include that data in the context in order for the agent to do something intelligent with that data. So real-time data really can only come in as context, not with supervised fine-tuning. So the talk is primarily about saying that context engineering is better than fine-tuning to get started, and is the dominant paradigm now for incorporating new data into LLMs, data not included in the training data set of the LLMs, because you can ship your improvements in hours instead of days. You can support real-time data. You don't need to retrain a model when a new frontier model appears. You can just keep your context engineering pipelines and your retrieval engines in place in your agent, and you just then replace your large language model version in the backend. And then the context data is very interpretable and explainable for both the users of these agentic systems and then the developers of them. That's some of the motivation for favoring context engineering. So what is context and how does it get there? We said that it's a subset of data that's going to be relevant for the query, and it will help provide a better response from the LLM. So in agentic infrastructures, we have an agent here. It has an API, and a client can issue a query via the API and get a response. The agent is now responsible for selecting the correct context data based on the query. So the agent can use a protocol like MCP, Model Context Protocol, to go to some RAG data source that stores context data. The data from there must come from somewhere. So often we'll have to build pipelines to get the context data from the sources that we want to use as context for our agentic applications and make that data available in a way that's easy to retrieve. Typically, we do that using functions at the moment. So LLMs can respond with, you can issue them a query and they'll respond with a function that you want to call via MCP, which can retrieve the context data for you. And that could be inserted into your prompt and then included in the prompt that gets sent, the context window sent to the LLM directly. So this looks very similar to people who are familiar with feature engineering. If you're building a machine learning model, we might have, for example, a feature store here, which has pipelines of feature data fed to it, and we use that pre-computed features to inject features into real-time AI models. So that's the kind of starting point for this. But the context data, as I said before, it's primarily going to be either private data that the LLM wasn't trained on, or recent data that was created after the LLM training cutoff date. So I'll go into a little bit more detail on the similarities between feature engineering and context for agents to get started. So if we think about feature engineering, we often say that, well, I need to use features to help train a model, and those features should have predictive power for the target or label that I'm trying to, if it's supervised machine learning, that I'm trying to train to predict. So the same is true for LLMs. If I have an agent, I only want useful context data. I don't want to just dump all the data in because LLMs can get confused. We don't want to have redundant data. So if I have a redundant feature, it'll make my model go a bit slower in machine learning. If I have redundant context, it can confuse an LLM. If I have an irrelevant feature, it won't have any predictive power, but it will make my machine learning system go slower, and it might reduce the quality of predictions. The same is true for context, but in context, we can also have the addition that the LLMs can interpret the feature values, the input context data. So you can have contradictory context where you have one claim, one piece of one fact maybe in one part, and then an alternative fact in a different part. So if those are contradictory pieces of information, it won't help the LLM answer the query correctly. Both cases, if I'm working in a kind of an enterprise environment, there's certain features I'm allowed to use because of the rights of the users of these models, the legal jurisdiction I'm located in, and the same is true for context data. You have, of course, data that you are not allowed to use in particular agentic applications. And then there's, of course, infeasible features. So maybe You can't compute the feature, it takes too long to compute, you won't hit your SLA, maybe the feature is leaky, or it's too expensive because it requires GPUs that your production system just don't have available. The same is true of context. It may be that there's some context information that would help your agentic application, but for some reason you can't retrieve it or you can't make it available in a context pipeline. So let's move on to a couple more similarities. We can look at what we call freshness of context. So we gave the example of TikTok, and maybe I click on a video or I share or like a video. So the time between you taking that action and that context being available for the agent to include in the prompt is what we call context freshness. And we have an analogy in real-time AI systems called feature freshness. So both of these are important concepts when it comes to building real-time agentic applications or real-time machine learning applications. How long will it take between an action being taken in an application to when that data can become available for use to make predictions with? If we go and look at machine learning systems now, and we talk about what does it mean to deploy a model for use by real-time clients, we can see on the bottom left we have a model here, and it calls model.predict. And the input to the model is what we call the model signature. So if you're working in machine learning, you'll be familiar with the fact that features that come in are typically represented in a numerical format. Maybe we have to normalize some features. If we have a gradient descent-based model that we've trained, we might have to one-hot encode certain categorical features, for example, for XGBoost, if you're using a decision tree. So the data coming into the model will be in this numerical format, but the clients who want to make an invocation, to make a prediction request, and in this example, this is from my book, the O'Reilly book that I've just came out now a week or two ago. We have a client that wants to predict credit card fraud. So they're going to send in the amount of the credit card payment, the timestamp, whether the card was present, the IP address of the terminal or the internet service, the credit card number, and the merchant ID. That's all the information that comes out, and we want to make a prediction if there's fraud or not. Now, that is not the information that goes into the model. So this API to our model deployment is not the same as the input or the schema or signature for the model. The input data of the model is going to be different. And the reason it's going to be different is because with this prediction request, this deployment API, we're going to look up pre-computed features using the credit card number and merchant ID. We're going to compute features using some of these request parameters that came in. And we're going to put them all together, and we're going to transform some of the feature data, and then we'll send that transformed feature vector into the model. And we're going to log all of the predictions and the feature values. So all of this means that basically models that you deploy, their API for calling them is not the same as the actual input signature to the model. Now, the same is true when you develop an agent. So often there's an assumption that because my LLM takes a query string in, and then we get a response, which is also a string. Now we know internally that the LLM will take a tokens in, but often you'll pass in a string, and a tokenizer will then tokenize that string for you. But the API is effectively, you can think of it as being a string coming in and a string coming out. But when you build an agent, you are not restricted to having that as your API. And this is important. What you can also do, and this is what I'll talk a little bit about later, is I can write an agent API that also includes, for example, IDs of entities. And I can pass those as context. I can say, for example, scan the last 7 days, and here's the customer ID. Do a primary key lookup, and here's the order ID. So if I pass that as additional context along with the query, which is it should be when will I receive my order, that query can go down to our agent, and our agent can use these entity IDs and instructions to retrieve context. And in this case, we don't necessarily always have to retrieve from a vector index. We can also retrieve, because we have primary key lookups and scans, we can retrieve from a relational database like a feature store that I'll talk about later. So we're able to retrieve all sorts of context information, not just chunks of data encoded in a vector index, but also enterprise data in tabular format from a platform like a feature store. So once all of this data has been included as context in our prompt, then we'll have the text API to the LLM, which will give us our response. So the agent API is not the same as the LLM API, as is the case for machine learning. Excuse me. So another comparison we can think of, and I'll give an example later, is that if an agent uses in-context learning, it's doing learning, do we not need training and test splits of our data? Because that's what we do in machine learning. In machine learning, when we train a model, we train on the train set, and then we evaluate the model performance on the test or validation set. Now, in agentic applications, how do we train? Well, training means in-context learning, and typically what that means is in my prompt, I'll include many different examples of the task or action I would like the agent to perform. So I give these as hints. We call those multi-shot examples. Multiple shots means many examples of the same thing. And then the agent, or say the LLM, can perform in-context learning with those as effectively the training set for your training or preparing the LLM to answer that question in the way you would like it to answer it. Now, when we have an agent and we're happy that we think it's working as we expect, we'd like to make changes to the agent and test if the performance of the agent is improving or disimproving. Then we'll look at evals. Evals you can think of as a test set that we run through our agent, and our agent gives us responses for all of these rows in our eval set. And then we'll score all of the responses to see if the agent is now performing better than before or worse. So we'll have a look about that in a few slides' time. So let's introduce evals first. And I mentioned evals are basically test sets for agents. So if I have an agent here and we have production requests, so request traffic coming into the agent will log all of these requests, including the response. We've got an input and output. The agent may take many steps to perform before it sends a response, so we can log all of the steps. But what we're able to do is score all of these steps. And the simplest one is to score just the request and response, but you can also score internal steps like looking up data from your RAG data source. So once we have our scores, what we can do is we can analyze each of these logged values and say, well, I can use some of these examples as evals because maybe my agent didn't answer as well as I expected. So I'd like to keep that one. So in future, I want my agent to answer better. And I can also get insights on how to improve the agent, maybe to add some instructions into the system prompt, or maybe how to get additional context data from a different store or the same store. So the evals are going to be that we can generate from the production traffic. You can also generate evals using synthetic approaches, but often it's good to generate them from production or expected production traffic. And then often you'll start by manually scoring a lot of these traces and collecting your evals. So the evals are really useful because they can evaluate the test set for our agent. They'll check its performance. I want to make changes to improve an agent. I want to check its performance. I'm going to run my evals. And it's going to store logs for all those evals. And then we're going to evaluate the performance of the agent on all these evals. Now, I mentioned earlier that you can evaluate that performance manually, and that's typically how you start off, by doing it manually. But over time, you have typically two different types of agent tasks. One are objective ones, where you might have an evaluator to say, well, did the task get executed? Maybe you check that the agent performed an action as expected. But we also have subjective tasks where an LLM can act as a judge. So you can automate this processing of running your evals and scoring them by having an LLM as a judge take all of these outputs and then writing these scores. Now, how do we get an LLM as a judge to perform well? We'd like it to know what is a good score for some rows, but what we can do is we can give a training set to the LLM as a judge. So once we've got our results of our scores, we can basically say, hey, the agent improvements were good or not, and we can accept the change or not. But let's look at how we do the LLM as a judge. So the LLM as a judge, we want to basically say to it, look, here are some good examples of requests and responses and scores. So we can pass them into the prompt of this LLM as a judge, and they'll end up being examples, so these multi-shot examples that we'll use for in-context learning. So when we have another row that we would like our LLM as a judge to evaluate, it will use these rows as effectively a training set for in-context learning, and they'll give you hopefully a better score. So this is a good way of evaluating the performance of your LLMs as a judge. Now, just to move on, what else can we talk about in terms of going from feature engineering to context engineering? And if we look at real-time context serving, and in particular of tabular data, so a lot of the most valuable enterprise data is stored in tables. And what we see at many of the large cloud vendors, their application architectures look something like the following. You have applications which generate data, and they typically go directly to a lakehouse table, so either through streaming architectures or batch. And from there, they synchronize the data with some sort of low latency context serving database. So for example, Databricks has something called Lakebase. And that gives you relatively okay query latency. You're going to have a query latency of 10, 20 milliseconds on Postgres. But the time it takes from your agentic application generating the event until it's available for serving will be minutes. So what we can say is the context freshness is not good. It's low. So what we need to do is we need to learn from real-time AI systems. So I work at a company called Hopsworks, and in Hopsworks, the applications can stream the data directly to the low latency context serving layer. So in our case, it takes sub-second to get the data from the application until it's ready and available for query. So you don't just have a low latency query, you'll also have very fresh context data. So 2 millisecond latency and then less than a second context freshness. That means you're really able to build real-time agentic applications. So I'm going to put this all together in the context of an agentic architecture, and this is covered in my book that I'll give a reference to later on at the end. But so context data will come from, I've talked about data coming from vector indexes and data coming from tabular data sources, and they're probably the two most important data sources. So the vector index data source is a very, very well-known one. You're going to have some documents or files up here. We'll have a vector embedding pipeline. So it's going to compute the vector embeddings over all the chunks, and we're going to have to chunk our data here. We'll store it in the vector index, and when a query comes in from our application, we'll use that query to retrieve similar chunks of data, and we'll include them as context in our prompt template and send them to the LLM. And this is a pretty well-known architecture. It's classically what people call retrieval augmented generation, or RAG. The user query string is passed directly to the vector index for a similarity search. Now, that's not the only form of RAG, because RAG just means retrieval. We can retrieve data also from tabular data sources. So one way you could think about doing it is, I have an application here on the left. It has its own application database. Can my application just retrieve the context data it needs locally? My application can basically say, I've got data related to an order, an article that I want to purchase, and maybe my user ID, retrieve that as context data, pass that with the query, and then hopefully you'll get a better response to the query from the LLM. And yes, you can do this, but it is the application developer's responsibility to retrieve and send the context data agent, and it does increase app complexity quite significantly. So it's challenging for app developers to write that code, and nowadays people are vibe coding a lot of these applications, and it's not that trivial to vibe code an application that's going to retrieve relevant context data. So what we've been working on with at Hopsworks is to try and have an architecture that makes it easier to retrieve this tabular data from application databases. So what we do is in Hopsworks, we can take application tables and databases. Either you can mount them in the feature store, so there's no copying of data. But if you, for example, don't want to issue queries directly on the application database, you can have, of course, pipelines. So feature pipelines that will compute features or context data and copy it into the feature store. So then the question is, well, how do I get access to that context data? How does my application reach agreement with the agent on what context data to include in the prompt? And our answer is to use entity IDs. So every application will naturally have some user IDs, session IDs, product IDs, order IDs, article IDs, and so on. And when the application issues a query, it wants to perform a task, it passes the relevant IDs. And the agent can then use those IDs via an MCP API to the feature store to retrieve relevant context and put it in the prompt. So what you can do here is, how do you know what the relevant IDs are? Well, your application will have a number of tasks that it performs that it needs help from agents from. So you can basically say, okay, for task 1, we need these IDs. For task 2, we need these IDs, and so on. And then we have the application entity data down here, which becomes available in our feature store for querying. So for example, if I have task 1 and I issue a query for it, the application will provide the user ID and the order ID, but the other IDs are not needed. So the agent will know to retrieve only the context data for these 2 particular IDs, user ID and order ID. And if you have a different task, like task N, it maybe retrieves user ID and article ID, and so on. So you have to decompose your app into tasks and then provide the appropriate set of entity IDs for each task, and the agent will then retrieve them from the feature store. We can also stream data from the applications directly into the feature store, and you can instrument your app to collect all of the actions and clicks and so on. And then within a second or less, the data will become available for retrieval. So a couple of slides left, and we'll be done. If we put it all together, and we put these 3 parts together, this is the kind of what is covered in the book as a kind of a semi-complete architecture for retrieving context information and ingesting context information for agentic applications. We have our vector index here, we have the feature store, and then you'll have other data sources for context like web search, external APIs, graph databases, and so on that we haven't included here. And of course, traces. Your agent should store its traces, and we provide support to storing them in the feature store. So what we're working on at HopsWorks now is we're working on this architecture. We have this coding agent called Brewer, which helps you build these pipelines to feed the data into the system and help you decompose your applications into these, your backend pipelines into these different components. And if you want to learn more, you can download a copy of this book. So I can offer a special kind of offer to people around the call. If you scan this QR code, you enter this promo code, PyData 2025, you'll get a PDF copy of the book. It's also available for purchase on Amazon if you prefer a paperback copy of the book as well. And I think with that, I'm on time, and I'll see if there are any questions. I'll leave this on the screen for the moment. If people have a look at it, and that's it.
Awesome. Thank you so much, Jim. We do have a couple questions. Let me see.
I think I'm still sharing. How do I stop sharing? Oh, there we go.
Yeah, there you go. Here we go. But here's the first question.
Okay, so we have, would an LLM as a judge over-evaluate another LLM? It feels like it would tend to be more positive, seeing that most LLMs are trained to be agreeable and supportive. I mean, it's a good question. So the general guidance people give is use the frontier, so the most powerful model as an LLM as a judge. If you're running evals, that can be expensive, right? It can cost a lot if you're going to just rerun your evals all the time. So at the moment, that's the best we have. Now, do they work? Are they completely, reliable? No. Do they have biases? Yes. I can't say all the biases they have. So will they because they tend to be nice, they tend to give good answers. I think, the challenge there, if you saw on the slide when I talked about LLM judges, yes, I can have this training set as kind of examples in the prompt for in-context learning. But if I want to evaluate them, I can have another test set that I run against the LLM as a judge and see how it performs. And if I change my foundation version of my LLM and see if it performs better, that's one way you can do that, to evaluate your LLM as a judge. But you often do it by hand. Sorry, that was my timer. So it's my 30 minutes. Okay. Hopefully that sort of answers the question.
Yeah, and that's perfect timing. Your timer worked out pretty well. Thank you so much, Jim. And if anybody has any other questions, please feel free to hop over to Discord and ask those. Any of the speakers or attendees are welcome.
There is somebody asked about the presentation is in the resources button on the left, so you can get a copy of the slides there. They're already there. Okay, thanks everyone.
Awesome. Thank you, everybody. Thank you, Jim.
Thanks.